Hello, Precalculus student. This video is for Chapter 4.7 Exponential Growth Model Part 2. I was doing example 2 in the first video about solving the system's equation when we were given two population size and two different time, but we do not know the continuous growth rate. We do not know the initial value. So we were almost done. So basically, we would set up this system's equation, solve for A0, plug into A0 on the second one, and to eliminate A0, so we only have K left over in the equation, and then we divide 200, so we have 7 equal to E to the power 20K. To solve for K, you just do ln, right? Because we want to move the 20K down or cancel the base. So the way you can do it is use ln. So ln E of 20K. So then the 20K would become a coefficient. So ln 7 would equal to 20K only because ln E is 1. Okay. And so K would be ln 7 over 20. Okay, so put in the calculator. I use decimal so you can see it. ln 7 over 20. So that would be our K, 0.0972996. So I use as much, at least 6 decimal places, because if we round too much, the number would be wrong. Okay, 0.0972996. So K would equal to 0.097296 after rounding, but we have to find A0. A0 would be equal to what? 200 over E of 10K. So put in the calculator again. So we do 200 divided by E to the power 0.097296 times 10. Oh, no, the times 10 has to be in the exponent, right? Times 10 here, times 10. So don't put it here. It should be the time 10, so 75.59. Yeah, in terms of, so you might want to round it to 76, but in order for the model to be more accurate, so I would say I would just keep 75.59. So the whole model would be 75.59 A0 e to the 0.097296 t. So this would give the population at time t. So what is the model to find the population after 95 minutes? So that's just plug in, right? So y would equal to 75.59 e 0.097296 times 95. So notice minutes, and that was minutes, right? So we were doing that. So I'll put it in here, 75.59 times e to the power 0.097296 times, okay, doesn't work. They always want a parenthesis if you're multiplying, times 90, 95. So just be aware if you're doing that. I think in the graphing, in the calculator, 781089 equal to 781089. So that's the population size round to the whole number. The last part, find the doubling time. So that would be easy. Doubling time is related to by ln2 over k, right? So it'll be ln2 over 0.097 296 in the calculator. Let's do it here. ln2 divided by 0.097296, 7.12 minute. which makes sense because the whatever that they give us at 10 minutes is 200, but at 30 minutes is already like how many times? Almost times five times, right? 30 minutes. So it turns out that because it doubles every 7.1 minute. Find the time it takes for the population to reach 12,000. So we use the model y equal to what is it? 75.59, right? E 0.097296 t. Now we want to find t if y is 12,000. Equal to 75.59 E 0.097296 t. So this is a regular exponential equation. Divide this 75.59 on both sides. So we have this number 12000 over 75.59 equal to E 0.097296 t. To solve for it, do ln on both sides. Ln of these things equal to ln of E 0.097296 t. So the whole exponent can move out in the front, and ln E is 1. So that means ln of this 12000 over 75.59 is equal to 0.097296 t. So to solve for the time, just divide on both sides, right? T would equal to ln 12000 over 75.59 divided by 0.097296. Put in the calculator, just a lot of typing. ln 12000 divided by 75.59, right? And then divided by, so 0.0, oh no, it's in the denominator. 0.097296. 52.08, so we can say it's 52 years. Or is it minutes? 52 minutes? 52 minutes. Yeah, because in 30 minutes it's already 14,000. It's already 14,000 or 1,400? It's 1,400, but every 7 minutes it's going to double, so it grows really fast. Yeah, 1,400. Okay, so basically that's how you do. The most important thing is to solve for A0 and K. Another population question, a population of bacteria double every 40 minutes. So we know the doubling time. The initial count is 600. That's very good. So we can just use the doubling count to double exponential function. So we would say this is A0, right? And this is the doubling time t. So we would say y or f of t is equal to 600 to t over 40 minutes. So this is the exponential function. You can also change it into to the the continuous function. We would find k, right? Find k. K is equal to what? ln 2 over the doubling time of 40, right? So you can say y is equal to 600 e to the ln 2 over 40, if you don't round, times t. So that is another way. If you want to calculate it out, it will be you do ln 2 divided by 40. Okay, so 0.017329. 17329. So we can write it down as 600 e to the 0.07, no, 17329 t. So this is also another one. What is the population after 70 minutes? So I'm just going to use the doubling time thing. So y equal to 600 times 2 to the 70 over 40. So put in the calculator, 600 times 2 to the power 70 over 40. 2018. The population will be 2018. Exponential growth can be used to also look at growth of monies by discrete compounding. That means compound a certain time limit. So we use, remember, A equal to P, open parenthesis, 1 plus R over N T. So this is the way we do compound interest. So there is there is a amount of money invested in an account, but compound annually. That means every year you only get one interest. So n is equal to 1. The rate is 2.5. So in decimal is 0.025. Right. So find the time it takes for the amount to increase to 4,000. Oh, I didn't write down what is this in the initial. So let's say 3,000 then. I forgot to write down. So 3,000 become 4,000. So what you do is you say 4,000 is the final A, right? It's A. 3,000 is the initial. And then 1 plus 0.025. Well, over 1, I don't have to do. And then T. So I need to solve for T so that it would grow to 4,000. That means grow 1,000 more for interest. That would take a long time, I think. So the first thing you do is rewrite it nicely. Equal to 3,000, 1.025 T. You can see that the unknown is in the exponent. We're solving exponential equation. Divide 3,000, divide 3,000. Simplify is 4 over 3, but don't around here. Just use exact value as much as possible. So 1.025 T, I want to solve this. Not enough space. So let's do ln because ln or log. We can do log because it's not e, right? 4 over 3, you go to log 1.025 to the power t. The t move out in the front. So t would equal to log 4 over 3 over log 1.025. Let's see how long it takes. So we will say log 4 over 3. This is inside the log. And then the divide by another log will be outside 1.025. It's 11.65 years. So that would be equal to 11.65 years. If the compounding is monthly, so instead of doing annually, but we do monthly. So what is the doubling time? Doubling time means it was going to do 6,000, right? Initial 3,000. 1 plus 0.025. So if you have monthly, every year you get 12 times of interest. So you divide your interest by 12 times, but you double more, right? 12t. So what is the doubling time? So this is the doubling time. That it would become 6,000. So divided by 3,000 first, so it become 2. 1 plus 0.025 over 12. So I don't divide this and round it because I want to use the exact value. And then to do this, I do log 2 equal to log of 0.025 over 12 and then 12t. The 12t can move to the front in front of the log. So I would have 12t equal to this log 2 and then over this log, right? Over 12. So then what would t be? T would be log 2. So don't put it in the calculator until divided by 12 and also log 1 plus 0.025 over 12. Do I have enough time to put in the calculator? So log 2 divided by log 1, log 1 plus 0.025 over 12 and also times 12, right? So 27.75. So it would take 27 years to double. We will look at another example in the next video.